I'm over at Lawrence Technological University, which is in Southfield, Michigan, if you're not aware of the place. But anyways, I'll be talking about the basic reproduction number, which doesn't seem to affect our community, but we kind of know about it, but maybe it does affect our community. So I'm gonna start going over with just basic models for biochemistry and epidemiology, as the title might allude to there. And I'm going to show how the basic reproduction number can actually be extended and be applied to biochemical examples, what the sort of context for that is, and what changes, what stays the same for those of you who are familiar with it already. For those of you who are not familiar with the basic reproduction number and how we use it, I'm going to be telling you, so you will get a full primer as a result. One thing to take away from this talk if you don't already know how that works. But I'll do some motivating numbers and sort of the extension, how that works, the second part, and then get into some of the challenges that still exist in this approach. So just as a little bit of background, something that most of us, I would imagine, are fairly well aware of. Certainly, this seminar focuses on the biochemistry part of this. So everything on the left here should appear pretty familiar, right? We have the idea of the network formulation in biochemistry or chemistry generally, where there's sets of interactions of individual molecules that meet, come together at certain rates to produce new molecules that have different function and that sort of thing. So this is a simple, what we typically call a futile cycle or a phosphorylation cycle. And when we put all those interactions together in our standard mass action ordinary differential equation framework, we get the rates controlling the dynamics in this way with a system of nonlinear ordinary differential equations. Um, if you are maybe a little less familiar, but I know a lot of people are familiar with mathematical epidemiology. We do kind of the same thing in a slightly different context here, but for epidemiology, we're tracking the spread of a disease or some sort of contagion in a population. So our basic molecules or people kind of, although the molecules don't change. But the interaction part of it's very, very similar. The network part of it's also fairly similar, although some of the context is a little bit different. Usually we represent it, a susceptible person becomes an infectious person through some transition. There's some transition web here. Not all these interactions are linear, right? We might have a facilitated, to become infectious, you need to meet an infectious person. So there's a nonlinear interaction there. But you get down to the differential equation part, and it is very, very similar, right? So you've got these sort of interaction terms on the right-hand side controlling the rates, first order system of nonlinear ordinary differential equations with polynomial right-hand side. You can simulate it, you can analyze it, all this sort of stuff you do to pass back on to your biologist friends comes from analyzing these systems. So very, very similar context. And despite that, though, there's not a lot of tools that generally just immediately apply from one pool to the other. And there's various reasons for that. I'm going to focus on one particular context. That context is going to be the boundary behavior. I'm just going to point out here that we are interested in the boundary behavior in both of these contexts. So in biochemistry, we are interested in whether a particular metabolite or molecule could tend towards zero over time, because that might tell you you're shutting down a metabolic pathway, right? You might be exhausting something. Maybe it's like hidden in the mechanism there, that it's not like obvious that you're exhausting it, but some sort of mechanism or a combination of different mechanisms needing the same resource or something like that, and it might use it up, right? And that would be kind of bad for our biochemistry setting. So we generally kind of want to avoid this. And we want to guarantee that our wiring of how things are interacting doesn't allow this to happen. So that would be, but anyways, that would be like the boundary behavior we'd be interested in for that reason. In epidemiology, it's like kind of the core thing, because epidemiology, we want to eradicate generally, we want to eradicate infectious diseases. So we want those infectious diseases, those I classes in our differential equations, to tend to zero, right? So that's the threshold difference. Does it go to the boundary or not? It's kind of the difference between does the disease survive or does it get eradicated. So it's a very, very important property of systems here, but it's important in both cases, and the setups are similar in both cases. And we're really just talking about boundary behavior. We're talking about boundary sets. So you can talk about mathematically a boundary set of the positive orthant is a face, right? So you might formulate it that way. So we have mathematical frameworks for these, and we have two very pressing needs for understanding what happens there for very similar models. So you would expect that there'd be more work on this, but or at least the connection between these two areas, but I'll explain why there isn't now. So the direct approach, how would you do if you had like just mathematically, I have a boundary equilibrium point or an equilibrium point in general, and I want to know whether it's attracting or repelling. Of course, we're going to have symbolic parameters. Generally, we're going to allow for that. The general thing would be, well, linearize, find the steady states, linearize around there. If it's a mess, maybe we get some lucky with the Routh-Hurwitz conditions. Those can often work, but it's often very challenging for, especially a significant number of symbolic parameters. You add a couple, more than one or two or three, it becomes fairly hard to read the Routh-Hurwitz table or compute the eigenvalues explicitly unless it's an incredibly small system. So that's kind of has been recognized in both of these areas is not the best way to go about doing it. Direct approaches aren't that helpful. So other things have been developed. In biochemistry, it's been largely a network approach. I've been kind of wanting to look at conditions like weak reversibility, endotoxicity, dynamic non-emptyability, other things that tell you something about the wiring of the network that says, hey, you can't actually go towards the boundary. Those structural conditions are enough to repel you from the boundary. So what starts positive is going to stay positive. We have a lot, you'll hear a lot about persistence and permanence in this context. Usually this is a keynote is that's parameter independent. We're talking about the structure of the system. We're not saying it's like, well, it is permanent for some set of parameter values and not permanent for others. We want it to be for every set of parameters. The wiring of the network is sufficient to guarantee that things survive. In epidemiology, it's a little bit different. The focus there has been heavily parameter dependent. In fact, the focus is on parameter sensitivity. We want to know in epidemiology, when can you drive something to zero, right? We want to drive those I classes to zero, and that's going to depend on the parameters. It's going to depend on the recovery rates, the transmission rates, the relative strengths of maybe different strains or whatever, or different population groups, heterogeneities, and that sort of stuff. Very different approaches here, right? So the biochemistry focuses on the structure, says, I want this to hold for all parameter values. Doesn't matter what parameter values. That's the way that we get rid of all this dependence on the symbolic parameters. Epidemiology, it's we take those parameter values and we find the bifurcation threshold value, the heavily parameter dependent basic reproduction number that tells us is the disease going to survive or not. It's a very different approach, and for that reason, there hasn't been a lot of interplay here, and we kind of expect. I'll say this, editorializing a little bit. You wouldn't expect the biochemistry approaches to work in epidemiology, right? You would not expect parameter independent survival or death of an infectious disease. That would be a weird model. The parameter sensitivity is like the key feature down here. So the parameter independent approach you wouldn't expect to work here. But maybe there are some cases where the epidemiological approach does apply in biochemistry, where there is parameter dependence here. We have to grapple with it. And the structural conditions we got here that have been developed aren't sufficient. And maybe epidemiology has something to offer in that case. And I'm going to argue that it does. But first, I'm going to give a little bit of a primer on what the basic reproduction number is and how we use it. So its most basic level, the basic reproduction number, which we denote as this R naught, is the expected number of new cases generated by a typical infected individual in a fully susceptible population. So it is that first person coming off a plane. I've traveled from an exotic location, wherever, got off a plane back to my home place. They've never seen the disease there. Everyone can get it. Nobody has any immunity. T equals 0. How many people is that new person expected to, in general, going to infect, right? So the higher that number is, the more there's kind of two consequences of this value. One is there's a toggle threshold, right? So if you infect more people, if you infect at least one person, the disease will continue, right? If you infect on average half a person or something like that, if it's less than one, that disease will kind of peter out, right? So it needs to be greater than one to spread, but also if that number is larger, right, 10 or something like that, that's a very contagious disease. You're infecting 10, one primary infection gets two new ones, right? And then that 10 becomes 100 and so on in like the short term. All right, so just for some context, here's the rough estimates on basic reproduction number for some common diseases. So you'll notice measles is way at the top. That's why also the higher this number is, the harder it is to eradicate in a population, as you kind of imagine. Like if even for perfectly vaccine responsive, vaccine controlled diseases, the higher this number is, the higher your vaccination percentage in the population is going to have to be before you really get that disease under control. So measles, yeah, huge basic reproduction number, 12 or 18 people in a fully susceptible population you'd expect per existing case, these many new cases. And then it sort of goes down. I mean, COVID was only really 2 to 3. That was the original strains. I mean, the newer strains with Omicron were much higher. At that point, it's kind of hard to estimate because there was a lot of immunity and other things in the population at that point. But yeah, so it was only 2 to 3, and we had that panic there. So we can see this is a very crucial number. Ultimately, we want to drive it less than 0, less than 1. So I'm going to give you a little bit of a primer on how this is computed, right? So that's a very statistical out in the field. Go figure out how many people um, are going to be infected each time one infection comes along. That's sort of mathematically, we want something that's based on our models. So I'm going to talk about a method called the next generation matrix method for computing the basic reproduction number. And this was introduced in 2002. So not as old as maybe you would expect, and it's basically a linear algebra approach. What we're going to do is we're going to we're going to find those infectious states in whatever our model is. We're going to focus on those. We're going to kind of ignore the other ones, like the S's, the people who aren't infected. We're kind of ignore them, and we're going to kind of create a map of how people in infectious states transition through that system. What we're going to do is we're going to divide the right-hand side of the infectious state differential equations into 2 parts, where we're just going to collect in the first part all of the new infections. So that every time there's a transmission event, we're going to collect those as this F vector. On the right, and the V, the other part, this negative sign is just there for technical reasons. Every other transition. So I just divide out the new infections and everything else. Then I take the Jacobians of these 2 parts of the system divided in this way. I take the Jacobian with respect to the infectious states. This F matrix, the F Jacobian, is called the force of infection matrix. The V matrix doesn't have any direct context, but we'll need some structural thing there. But the inverse of it is very important. The inverse of the Jacobian of this matrix is the dwell time matrix, and it actually does correspond to the amount of time people would expect to dwell in each one of those states. It's a stochastic sort of thing. The next generation matrix from which the method gets its name is this FV inverse. We just multiply those together. The basic reproduction number miraculously ends up being the spectral radius of this matrix. So take all that in if you haven't seen it before. If you have seen it before, here's a little concise, note card size, review of it. The key thing here is the F and the V inverse. In the epidemiological context, it's like F is kind of like how many new infections does each person give in an particular infectious state. The V inverse is how long are you going to be in that infectious state. So it is kind of telling you how many new infections there are going to be across over all possible states that can give new infections. Turns out the spectral radius is what we're going to need for things to continue there. So there you go. Take it in. I'm going to move on. So I give an example here. So this is the SIR model that we looked at a little bit ago that probably most people have seen before. Now we're going to do this. I'm going to make the analogy with boundary steady states, because that's really what we're doing on the mathematical side of things. So the boundary steady state, you can check is SIR is the S will have some content. So there'll be some people who are susceptible. And then there will be an I and an R. There'll be 0, right? There'll be no, if you've got the disease-free state, the I is people who are currently infected. The R is people who are recently had it, but haven't lost their temporary immunity yet. So they've recently infected, but temporarily immune. So I'm going to take I and R. It doesn't matter. It might be more natural to take I as the infectious class, but I'm just making the analogy with the boundary states. So I'm going to take I and R. We can split that system in this way. So the new infections are, let's see if this works. I can grab the new infections. Oops, nope. The new infections are just this part. I'm going to focus on these 2 equations here because those are our infectious states. And I'm just going to grab, for the F, I'm just going to grab that. That's the only new infection term there. So I put that in our F. Everything else goes in the V. Right, so everything else, I do have to change the sign, so it's minus V. That's just for technical reasons. So don't worry too much about that. Then I compute the Jacobians. So I take the Jacobian of F and V, and then I take the inverse of this one. I compute the product of F and V inverse. That's this. The spectral radius, of course, well, that I can just read out now. It's just going to be that entry. And that is what you would expect to see, or something like that, for the basic reproduction number. This, again, the threshold value is 1. So if it's higher than 1, disease is going to spread. If it's less than 1, disease is not going to spread. So right? Beta here is the transmission rate. So yeah, increase that, more likely the disease will spread, right? Or if you on the bottom we have the that's the recovery rate. Or no, is it the recovery rate? I'm trying to remember what the old system is. A couple ways of doing it. How did I have that written over here? Oh, death rate. I had this one with death, right? So this one, death rate and recovery rate. If those things go up, those will actually decrease the spread rate. As you can be, that'll drive that lower towards one. Right, so we can see the infection here less than or greater than one. If we want it to die, we need to ensure that this quantity goes less than one. But we get it from the model. It's very nice. You can make the model as complicated as you want, and you can do this process. You get the values. It's a little bit of linear algebra. It's very, very nice. Um, and it basically, we want to think about, well, could this help us in biochemistry? Right? So let's think about this. Can the next generation matrix method be applied to establish boundary steady state stability for examples from mathematical biochemistry? We also have boundary steady states in biochemistry, and we would like an easy way to figure out whether they're stable or unstable. So I'm going to consider this example. This is simplified from the ENVZR-OMP or ENVZ-OMPR system from the famous Shinar-Feinberg paper um, on absolute concentration robustness. So it's a little bit simplified. It's got a little bit less, and it's only 6 reactions. It's got these 7 species in it, a few intermediates popping up in there. Well, notice it does. I choose this one here as the illustration because it can't really be represented. There's some epidemiological models can be represented as biochem models. Some biochem models can be represented as epidemiological models, just with a different interpretation of the species. This one is really hard to do. You can't really interpret this as a epidemiological model because you've got things like this where two things come together to form one thing. That doesn't happen in epidemiology. You don't have a susceptible person and an infectious person coming together, joining hands, and becoming some new thing, some new person, single person. That's just not how that works. All right. So some of the interactions here are a little bit different. At any rate, you get this set of differential equations. We want to see, well, let's look at the boundary and see if the next generation matrix method can help us here. So the corresponding boundary state, you can just compute this. I do have 2 conservation laws, one in X and one in Y. The other stuff I have here is I have these 0 states. These 0 states correspond to our infectious stuff. They're the stuff we'd want in the epidemiological model. We'd want them to go to 0. These are the infectious states. Now they're just random species in the system. But we're going to start there, right? So I'm going to treat these as though they were the infectious states, the ones that go to 0, the ones that I'm trying to eradicate, I guess, in the epidemiological sense. So this is my set of those species. Right, so I'm going to focus on those differential equations. I'm going to split the system. Now here, again, we don't have any epidemiological interpretation of this thing. So I don't have new infections. No infections doesn't mean anything in the biochem setting. You can try to wriggle around there and say, like, this is what a new infection is. This is what a new infection is. I'll explain why in a little bit. That isn't that helpful. But anyways, I'm going to kind of do away with this new infection thing is let's just pick a term on the right-hand side of the differential equation. So here I picked one of them somewhere in here. Which differential equation did I look at? I looked at the xpy prime, xpy prime. So I picked this term. This is a positive term. So I'm saying this is like my new infection term, right? It's not, but I'm going to let that slide, right? It turns out we won't need that. All right, so I'm going to let that be the F. Everything else is becoming part of V. I can take the Jacobian of those 2 matrices as just a single term, because a single thing I took into F. A single thing for this. I evaluated at the boundary steady state. That's why these Y, the total values of X and Y pop in there. But that's all fine. I can do that computation. I can compute the inverse of this. I haven't displayed that because it's messy. But I can compute the product of that and the inverse here to get this matrix. Spectral radius turns out to be this. This is like our basic reproduction number. Did it work? It did. It actually did. You can check explicitly that, right, R not greater than 1, that's when the boundary steady state is repelling. That's when the disease survives and then nothing goes to the boundary. That happens if this is greater than 1. If I go back here, I can set this greater than 1, rearrange for YT. A little bit weird because we got this biochemical conservation that's happening here, but this is actually true in every conservation class. where the conserved value of y is greater than k2 over k5, it is unstable, and every one where it is less than this value, it is stable, right? I actually have a conservation law dependent switch in stability. It's actually worked. The question is, does it always work? It'd be great if this always worked. And of course, it's always a little bit complicated for some reasons I've alluded to and some reasons I have not. Right, because the context in biochemistry is a little bit different. Where it's important, but some of the details need to be worked out. To understand why it may or may not work, we need to understand why the next generation matrix method works anyways. So that is here. So there is mathematical theory on the splittings and why it works. So what you need here, the things that were important, I do need a subset of variables to go to zero. That's all I needed. So that was the same for epidemiology and biochemistry. I looked at where are the steady states where it was zero. I need F to be non-negative. So I had that for free in the epidemiological context because it was new infection. So those are always positive. That term here. I need V to have a specific sign pattern. It needs to have non-positive off-diagonal entries. So that's going to be something we check. And I need V to be invertible, first of all, and then I need it to be non-negative, right? But if I have this set of things, I don't need anything more. I don't need any of the new infection stuff. I don't need any of that epidemiological structure. None of it was necessary. The epidemiological structure just guaranteed this was true. So what we need to do is think about how this can be updated to the biochemical setting. But if you have this, the result, and it's kind of actually surprising if you haven't thought about it before, and maybe even if you've used this extensively, what we're doing is a linear stability argument. This is the breakdown of the Jacobian. The Jacobian is actually F minus V, right? What it's saying is like the real part of the eigenvalues of F minus V must be somehow related to the eigenvalues of F times V inverse. That's actually a little bit of a stretch, right? It's not an immediate thing that should be true. It is true if these conditions are satisfied. It fails if these are not satisfied. These are the crux of it, these conditions here. So epidemiology, you get it for free. Biochemistry, we'll have to think about it. I'm not gonna worry about I don't want to go over time. So adapting to the biochemistry setting, if you want the zeros, they're not gonna be infectious sets. We know the zero set does have some work done on it. So I've been referencing the work on siphons. So you can determine the zero set for the boundary in biochemistry by looking at the siphons. So you can get that from the network structure. So that's something that we can get. Those are kind of like the siphon is like our infectious states now. And I'm just adjusting some of the underlying language here so those conditions a few slides ago are satisfied. And so as long as those are satisfied, this works in biochemistry as well as it does in epidemiology. There's some little cleanup you can do with the conservation laws if you want, because we do have those. Epidemiology doesn't generally have to worry about them. But really, how do we guarantee that these things are positive? This is the crux of it. It's automatic in epidemiology. If you basically assume you have an infectious disease spread under any reasonable conditions, that's what you're going to see. For biochemistry, it's more challenging because you have these non-epidemiological things, like things that can bind together or disassociate, go in the other direction. You also have conservation laws that can sometimes throw a wrench in things. So there are some results that I've been able to come up with. They're not exactly as intuitive as just saying it's like, oh, just pick the new infections. But you can do this with different examples. So I'm trying to stay on time here. Maybe if I can have like 2 minutes, because I do want to go to one complication that comes up. Maybe do one example. Actually, maybe I'll skip to like the full, because it's kind of crazy that this works, but it does. When it does, it does. This is the full model from the Shinar-Feinberg paper. So it's got more to it. I've included the reversible reactions. What you need to do here is you need to look at the zero sets and then compute the next generation, do the next generation matrix stuff. Right. So here's the siphons. You can get that from the network. There is a yeah, these will be the variable. In red will be the variables that go to zero. Everything else will not at steady state. So I have here, I can compute, they're too big to show, but the F is big, but it's non-negative. I need that. The F inverse is big and non-negative. Here's the structure of the V. I can actually put that there. It does have the sign structure where it's non-positive on the off diagonals. Right? That is a sign structure we do strictly need for the result to hold. After a bit of work, you can put the F and the F inverse together it will be a sparse matrix, and it will have this as the only relevant eigenvalue. And then you can just invert it and say it's like, okay, well, when will this survive? When will the species persist? And you put, you know, do whatever you have to do with your science to get that to work out. So you'll notice here, this is actually the ACR value. So you have a compatibility class dependent ACR value, but you get exact theoretical correspondence, right? So this greater than or less than one exactly corresponds to linear stability of that boundary steady state 100% of the time because the conditions are satisfied. So it's very strong. It's not like wishy-washy in some parameter regions. It's a complete analysis of this particular example. There are some things that can happen though that make this a little bit more challenging. So optimally splitting the system is a problem. The choice of the F and the V are not as clear. We don't have a notion of new infections. So if I take that last example, the full ENVZR or ENVZ OMPR system, um, I don't have a new infection system, and you might wonder, it's like, oh, there must be a best choice here for the yeah, I just need F to be positive. So okay, well, I've got these candidates for the positive terms here. Well, I can just do a quick enumerative thing here. There are about 16,000 possible combinations of these particular terms here, the 14 positive terms over there, that I could choose to put in F. And you might wonder, it's like, oh, just pick the smaller ones. It's like, no, 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 no. Some of them work and some of them do not. Some of them violate the conditions that we need with F and V and the sign structure and invertibility of V in particular. Some of them do. So we need to be able to find a way to pick them so that they necessarily work, that V is necessarily invertible and positive. Not all of them are. And even if they are, you can get different values, right? So depending on your choice of splitting for F and V from that set of 14 possible choices for F, I can get different reproduction numbers. Now, in epidemiology, this would be a terrible thing. They've recognized this before. It does happen in some of their models too. So this is the one I gave before. This was taking one choice of the terms from the red and the last thing. Another one, I can get this value. I can also get another one. I get this value. They get gruesome. This is only up to second order. I can get fifth order roots here. All of these values have the same critical threshold of greater than one, less than one. That is guaranteed by the mathematical theory that underpins this. You will have the same bifurcation value, right, at point. But you get different values here. The thresholds will be the same for stability and instability, but the values are actually very different. I'd much rather deal with the first one than the second two. I don't know a way in general to guarantee that that happens, right? So that's one piece of work here. Also interpreting what these values mean in the biochemical context. Could use a little bit of work there, but at any rate, it does work. And I will say I haven't emphasized this, but it's significantly less work. You can't do any of these models doing a direct find the eigenvalues approach, or even the Routh-Hurwitz tables. They're gruesome. This is kind of actually necessary if you want to do it. It works, and it's really kind of the only available option as far as I know for these kind of systems. But there's stuff that we need to do on figuring out how it works, when it works, all that sort of stuff. So thank you for paying attention.